WDM in optical networks is widely used, either in the large version or in the micro-optic version. But how does it actually work? If you want to find out, stick around and we'll check it out. Today I'm focusing on thin film filter technology, and I'm using the example of a demultiplexer. This always means we are talking about a cascade of filters, and this is depicted in this sketch here. So the rectangular shapes are representing the filters, and here is the common fiber where all the different wavelengths are incorporated in or guided in, and they are entering the filter. One wavelength is passed, in this case it's the green one, the rest is reflected, goes into the next filter, one is passed, the red one, and so on and so forth. This is the basic principle to divide all the different colors completely passively in, for example, separate fibers. So now the question is, how does such a filter work, or what are the requirements for such a filter? And for that, we have to take a closer look to such a spectrum. It's an optical spectrum. In this graph, you can see on the vertical axis we have the transmission of the filters. It goes from 0% to 100%. And on the horizontal axis, we have the wavelength in nanometers. Depicted here, you can see the example of 5 CWDM channels. Basically, we have two types of filters. One is the edge filter, and the other one is the passband filter. Let's take first the edge filter. This is the example of an LWP. This means a long wave pass filter. And if I put it here over the spectrum, you can see ongoing from this edge, all the higher wavelengths are passing, and all the wavelengths which are below this edge, they are reflected. There's a similar version of that, is the so-called SWP, is the short wave pass filter. It basically makes the same, but vice versa. So this means higher than the edge, all the wavelengths are reflected, and below the edge, they are passing. Obviously, by design, you can shift this edge position. So this means you can determine if the filter edge is here or it's a little bit higher or lower. But now the question is, you can see we are not able to find only one or separate only one wavelength, one channel. And for that, we use the so-called passband filter. If I put this passband filter over the spectrum, it becomes obvious that it is open, or it's transmitting all the wavelength 1311, and all the wavelength above and below this target channel, they are reflected. And this is exactly what we're looking for. By designing the filter in the right shape, you can determine which of those channels is passing, and this is how we can realize such an filter cascade as I mentioned before. The question that remains is, what for do we need such an edge filter? And for that we have to take a closer look to the, let's call it reality. Such a passband filter, it's more or less impossible to design it in a way that all the wavelength higher than the target wavelength and lower than the target wavelength, that they are all reflected up to infinity and down to whatever it is. So this means a real filter gets a little bit open if you go to, for example, higher wavelength. And this would be a problem isolation-wise in your system. And that's the reason why you can combine two filters. So you take this passband filter and combine it with, for example, this low pass filter. And as you can see, the opening wavelength of the filter in the higher region, they are blocked away because they are not available due to this low pass filter. In principle, the whole topic on filters is quite complex, and there are numerous points we could discuss. So if you're interested in certain topics, please feel free to give us a hint in the comments. And for all the other people, I hope you learned something today, and see you in one of the next videos. Bye bye.